Hi, so I'm going to be going over the count primes problem and solving it using the umpire method. So to start, let's just read it and understand it. So we're given an integer n, and we're asked to return the number of prime numbers that are strictly less than n. So if n is prime, it doesn't matter. We just want to go anything less than n. So it gives us some examples, and this helps our understanding. We're given an input of 10. We have 4 because there are 4 prime numbers less than 10. It's 2, 3, 5, and 7. Conversely, if we're given n equals 0, that's just going to be 0 since 0 is automatically not a prime number. Likewise with n equals 1. And then, of course, here are some constraints that we have. So I already think that I have a pretty good understanding of this. I understand how primes work. Um, I think moving on to the match step, this is probably going to involve some looping, probably an array to store some of our results that we can sum up later. So I think I'm ready to go to the plan step. So let me just write some comments here. Um, so first, we're probably going to need a list just to store um, our we're going to need to store whether a certain number is going to be prime or not, and we can use booleans to be able to represent that. And it's going to be a list that's going to be um, of length n, and we're given an input already, so we don't have to worry about asking for the input. Um, and then I think what we're going to have to do is it'd be easy to just set all of these values to true. And we're using the index values for the numbers. So we're going to set this all to true. And then since we already know that 0 and 1 are not primes, we're going to start looping from 2. So we're going to loop starting from index 2. And then I am going to use the sieve algorithm. I forget the full name, but I think that's the most efficient way to solve this problem. So since we already know that if we were to start at 2, all the multiples of 2 after that would not be prime. Same with 3. Any multiples that we know are not prime. So we're just we're gonna have 2 loops, one starting from index 2, and the rest are going to be multiplying through it just to check. So in this inner loop, we're going to set m. We're going to use m equal to the index, and then we're just going to go through all those values. So 2, 3, 4, 5. We're going to multiply it by it, and then once we do that, we're going to set those equal to false in that list. And then we're going to want to increment this index. And then so we do need a condition to break out of this. So if m is greater than n, then we can just break out of it because we don't want to exceed the maximum. Okay, so that's sort of my plan so far. I'm going to go ahead and just start converting this to code. Um, so for our list, I'm going to call it is prime. And it's just going to track all the prime values, initially set them to true, and we're going to multiply this n plus 1. Oops. And then we're going to use while loops. So I'm just going to set an index counter, and we're going to start it at 2, and then a while true loop. Since we already know that if we're going to use the sieve algorithm, we don't need to go past half of whatever the half of all the numbers is in our input, because we already know that we can check or deduce that they're not going to be prime. So that could be a condition that we initially start off with. If the index is greater than n divided by 2, we're just going to break out of that. And then I'm going to have another counter to start our inner loop, k equals 2, and another while true loop. And we're going to set m equal to index times k. So you can see here, we're going to eventually increment this, but if we're going to start at 2, for example, it's going to check 4. It's multiplying. And then once we increment, it's going to check 6, 8, 10, and then eliminate those as primes and set them to false. So to do that, well, first we want to check if m is greater than n, then we know we've reached the limit. So we also want to break out of that. And then, yeah, and then we're gonna want to set this equal to false. And then we want to increment k. So k equals k plus 1. And then after this, we want to set the outer loop index. We want to increase it since we're done checking 2. So we're going to do index equals index plus 1. And then this is sort of the bulk of the logic, but if we're going to the next numbers, we want to check if we've already turned them false. That means we can skip over them since they were already checked. So I'm going to do another loop right here that's going to say while is prime at that index equals to false, index equals index plus 1. So if it's true, or if it's false, we want to keep going and check one that is true and we haven't checked yet. So that's the main bulk of it, but we still need to count how many in this list are true or false, or we want to count the primes, so whichever's true. What we're going to do is do another loop down here and set a count variable equal to 0. And then for I in range 2, and then we don't want to go up. We want to, like the problem stated, we want to go less than n. So we don't want to do n plus 1. We want to do just n, and it's exclusive, so it won't go up to there. Um, and we're going to check if um, is prime is equal to true. We're going to increase that count variable. And then after that, we're going to return count. Okay. So this is a full working solution that I've actually already tested. But just to go over sort of, just to evaluate it, we can say that the space complexity is going to be O of n, since if we're given a bigger number, we're going to be handling a bigger is prime array. This is just going to grow at an O of n rate. Also, this outer loop is going to be O of n because it's similarly, if this list is growing at an n rate, this is also, it has to go through all of them. While we do check, while we only go halfway, that would be O n over 2, which we can ignore the 2. But this is more efficient than just a more basic solution, because um, right here, when we're going from each subsequent number and checking multiples of it, it's going to be, O of n over 2, n over 3, n over 4. So it's going to be logarithmic. So we can say overall this is going to have, I think, an O of n log n solution.